Assalamu alaikum and welcome to lecture number 23. In this lecture we are going to discuss the basic structures for the FIR system, and we also start the filters. So for the filters I'll be using the book Digital Signal Processing, a Practical Approach by Emmanuel I. Fetcher and Barry W. Jervis. So let's start. In the previous lecture we talked about different forms of the IIR system. You know, these different form results when you express the system function in different forms. So for example, if we express the system function as a rational form, so we have direct form of the structure. Similarly, if we express it as in the factored form, so then we have the cascade form of the structure. Or if we expand the system function in partial fraction, then we have the parallel form of the structure for IIR systems. In this lecture we are going to talk about the basic structure for IIR system. So you understand, for a causal FIR system the system function has only zeros, and it has a pole at z equals to 0. So the generalized linear constant coefficient difference equation is this one. So in this case, because we have only zeros, we don't have poles, so that means the coefficients ak will become 0. So when they become 0, the resulting equation for the output will just consist of the zeros. You understand, poles at z equals to 0, but the rest for the rest of value it will consist of the zeros. So this reduced expression for the causal FIR system, if we carefully observe it, we can see that it is basically the discrete convolution of xn with bk, right, where bk are the coefficients. So we can write this bk as h of n, or the system response, where h of n equals to bn for n equals to 0 up to m and 0 otherwise. So recalling the direct form 1 and form 2 structures for the nth order IIR system, we can see this one was the direct form 2 structure. I hope you can differentiate between the form 1 and form 2, because in case of direct form 2, that is canonical, it uses the minimum number of the delay units or the memory. Whereas if we talk about the direct form 1 structure, there we have double of the almost double of the memory units which are required. Also, if you recall that we know by just looking at the figure, so you see that in case of direct form 1 we implemented poles first, and then in case of and followed by the zeros, whereas in direct form 1 structure we have zeros followed by the poles. And this swapping or shifting of the zeros and poles is due to the fact that the systems are linear and time invariant. So that means you perform first one thing, right? You understand the condition of the linearity, that is the support, right? So for a system to be linear, it should obey two properties, or should hold two properties, that is scaling and the superposition. Okay, so I hope that we have done this, but just a recall, because we need the structure for IIR, direct structure for IIR. So by looking at the figures you can easily tell, because in case of IIR we don't have poles, that is these coefficients a1, a2, these are all zeros, or also this one. So we straight away result into a direct form 1 realization by just removing the poles, right? So if we remove the poles, we are just left with the zeros. So that means for the IRI, for the FIR case, we don't have this, and we also don't have this. So that means we have just, if you look at this one, so we have the just zeros. So on comparison, you understand that B0, B1, B2, these are all zeros, right? So they are represented by h of 0, like B0 represents h of 0, B1 is represented by h of 1, h of 2, and so on. So we have here, if you look at this one, at this node, we are just adding them. So we have at this node B0 x of n plus B1 x of n minus 1, right? You understand this is delayed by 1 unit. So at this point, we'll have B1 times x of n minus 1. At this point, we have B2 times x of n minus 2, and so on. So if we look at this one, so here again, we are adding them. So that means here we'll have x of n. At this point, we'll have x of n times h of 0. Then we delay it by 1 unit and multiply or scale it by h of 1. So we'll have h of 1, x of n minus 1. Here we'll have h of 2, x of n minus 2, and so on. So if we look at this figure, on the top we have a chain of delay elements. So this structure is also referred to as a tape delay line structure or transversal filter structure. So applying a transposition theorem similar to what we had for the IAR system, the resulting structure will be this one, right? So you understand, in case of transposition, we replace the input by output. We change the direction of the arrows, right? So if we have x of n, now it's going this way because in the original it was going downward, right? So it's going upward, and then we have the delay, and then we again have upward, and so on. So I hope that's also a straightforward thing. So if you have any confusion, we can discuss it in the class. So I hope that's straightforward, that in case of FIR system, because we don't have poles, so we remove this part or this part, and the resulting structure is quite straightforward. So this is called the direct form 1 realization of the FIR system. So just like we had expression for the cascade form for IAR system, we can also have a cascade form for the FIR system. And if you recall, to obtain the cascade form, we represented the system function in the factor form. So similarly, for the FIR, by expressing the system function in the factored form, we can obtain the expression, this one that you understand, this one is the expression, system function expression for the FIR system. So representing it or expressing it in the factored form. So here we have the second order system. So B0k plus B1k z inverse plus B2k z inverse power z power minus 2, right? You understand, we can expand this one. So we can expand this one. I hope you understand. So by putting different values of k, we can get factors running from 1 up to ms, where ms is m plus 1 divided by 2, and this symbol represents the we take the largest integer contained by this one, right? So if we expand it, so we'll have something like b01 plus b11 z inverse plus b21 z power minus 2 multiplied by b02 plus b12 z inverse plus b22 z power minus 2 multiplied by b03 b13 z power minus 1, b23 z power minus 2, and so on. So in this case, if m is odd, so that's quite straightforward, that we'll have one of the coefficient b2k that will be 0. So the signal flow graph for the equation is shown in figure here. So here we have shown this the signal flow graph represented by the above equation, this equation. So if we compare this with the cascade, right, this is the cascade for the system, right? So if we compare this one with the one we have discussed for the IIR system, so this is again the same similar graph that consists of the second order sections, right? So if you look at this one, we are removing this one, right? So we, in case of the FIR system, we don't have these poles, right? So simply it reduces to this one. So I hope you can easily compare that the left part, right? This one is the left part. So we just remove the left part. Okay, so we just don't have the left part, so we straight away have x of n b naught 1. So again you can see x of 1 b naught 1, but because this part is removed, so we just have a delay and b11, right, which is summed here, again delay b21 and summed here. Similarly for the second section we have b naught 2. Okay, so again if you look at this one, so we are just because these are FIRs, we don't have the poles, so that means if you understand the previous one, that will be quite straightforward to grasp the idea for this one. So I think in similar way we can do. Okay, so I hope that's also quite straightforward, because it's similar to what we have done in for the cascade form of the IIR system, but it is simpler in the sense that we don't have poles, so we have this diagram. So the next topic we are going to discuss is the linear phase FIR system. You know, the linear phase causal FIR systems have generalized linear phase if the impulse response satisfies the symmetric condition. So if you recall that based on this, we had 4 types of the linear phase FIR systems, right? In the type 1 and type 2 we had symmetric response, whereas in case of the type 3 and type 4 we had antisymmetric impulse response. So with these conditions, either for the type 1, type 2 or type 3, type 4, the number of coefficients multiplier can be essentially half, because you understand they have the response is symmetric or antisymmetric, so the number of coefficients required are halved. So let's take the example when m is even. In that case we have y of n equals to summation k running from 0 up to m, and this is the generalized expression, but for the case of the even symmetry we can write when m is even, not the even symmetry. So when m is even, then we can write that this summation can be expressed in 2 halves. One half was from when k running from 0 up to m by 2 minus 1. So we have h of k, x of n minus k. Then we have the value for k equals to m by 2. So we have h of m by 2, x of n minus m by 2, right? And then we go for the value when k is equal to m by 2 plus 1 up to m. So we can split it into these 3 parts when m is even. Okay, so let's change the variable here. Okay, variable of summation is k. So if I say k equals to m minus l, so that means l equals to m minus k. That's straightforward, right? Now when k has limit equal to m, when k equals to m, so we replace k here by m, so m minus m, we have L has limit of 0. Similarly, when k equals to m by 2 minus 1, then because L equals to m minus k, so that means we'll have m minus m by 2, and because all minus here and this one is also minus, so we can write it as plus. So we can say L equals to m minus m by 2 plus 1. So m by 2, m minus m by 2 results into m by 2, and m by 2 plus 1. So we have this. Okay, so now we can write this expression where it was k running from m by 2 plus 1 up to m. So now we have L running from m up to 0. We have k here. Now k equals to m minus L, so I'll write m minus L. And then we have the second term, that n minus k. So k is basically m minus L. So because k is minus, so that means we'll have minus m plus L. So x of n minus m plus L, right? So we have this expression. Okay, and because you understand that we are summing it, there is a difference between integration and summation. Because integration you say, okay, upper limit minus lower limit. So when you interchange the limits, in case of integration you need to put a minus sign, but in case of the summation, because we are just straight away summing them, either we sum from m running L running from m up to 0, or from 0 up to m, it will result into same. So that means I can straight away write that L running from 0 up to what is the sorry, that was mistaken, I think. Yeah, because I wrote it wrong. It was basically this one, m2 m by 2 plus 1. So lower limit, upper limit is this one, right? So I can straight away write m by 2 plus 1. Again, I can change the variable of integration, summation. So if I sum it, L running from 0 up to this, and we have L here, if I replace L by k, I hope it shouldn't affect anything, right? So if I replace L by k, right? So now because we say L running from 0, then k is running from 0, and upper limit of L is m by 2 plus 1, so this will be m by 2 plus 1, because you understand there's no change, right? So whether we use the variable L or k, so if I replace the L by k, then I have this expression. Okay, so I hope that's clear to you. Now, because we know in case of type 1 we have the even symmetry. Okay, so that means h of m minus n equals to h of n. Similarly, for the case of odd symmetry, which we have in case of type 3 or type 4, so in that case we have h of m minus n equals to minus h of n. Okay, so for the case when we have even symmetry, that is type 1, then we can write this as it is. You understand this one? Okay, and because for the even symmetry, h of k equals to h of m minus k. Okay, so that means instead of using two summation, we can use a single summation, because these coefficients have same value. Thus we can write y of n equals to k running from 0 up to m by 2 minus 1, h of k into x of n minus k plus x of this one, right? Because we have different values for the input signal, we have only the symmetric impulse response. So we write h of k multiplied by x of h of n minus k plus h of n minus m plus k, right? So because we can take the summation common, because it's the same summation here, so we can take as common. Also because these are same, h of m minus k basically equals to h of k. If you look at this equation, okay, we have just k. Okay, so I mean, if I write n, then I can say, or if I replace k here, I can write h of m minus k equals to h of k, and then I write k running from 0 up to m. So I hope these variable doesn't disturb your concept. Okay, so that means we have this. So we can take this summation form, summation common, and also h of m minus k, because h of m minus k is same as h of k. So we are left with this thing. Okay, we are left with x of n minus k and x of n minus m plus k. Okay, so we can just add them here, and you understand that we have taken. Okay, so we have something like this. Okay, so we have taken h of k as common and y common. That's I hope that's clear to you. So the third term, we have this one. So I've just mentioned the third term here. So I hope that's quite straightforward, right? We just change the variable, and just based on the fact that the in case of FIR, causal FIR system, the linear if the impulse response satisfies the symmetry condition. So we have done this in the previous chapter, that we have two types of symmetries, that is a symmetric impulse response and anti-symmetric impulse response. So in case of symmetric response, we have this thing, and in case of anti-symmetric response, we have this. Now, to derive these expressions, we have assumed that we have m even. So for m is even, we have this derivation. Now let's come to the second part. Now for the case of the type 1 systems, because you understand type 1 and type 2 have m equals to m is even, and type 1 is symmetric, whereas type 3 is anti-symmetric. So for the case when m is even, we have this expression for the type 1 system. So you can see that we have essentially reduced the multiplier to half. For the case of type 3 system, because in that case, instead of h of k equals to h of m minus k, in fact it is h of k equals to minus h of m minus k. So if I place minus here, then I'll get something like this one, minus sign here. Okay, because the h of k and h of m minus k, they are anti-symmetric, so we'll have a negative sign here. Also because this term is 0 for the anti-symmetric case, right? So we straight away have this expression. Similarly, for the case when the m is not even, in that case we have the upper limit as this one, right? And we don't have this term, also the middle term. And I hope straightforward is for the type 4, where we have this expression, because again m is not even, so in that case we have the upper limit equal to m minus 1 over 2, and again we don't have this term, so we straight away write, or perhaps you can just say straight away for the because for the case of type 3 we have this expression. So in case of type 4 we just have the change of limit, because m is not even, so that means m minus 1 by 2 will be the upper limit. So I hope that clears your concept. That's very straightforward, that we just exploit the properties, right? And the properties are that the causal FIR system with generalized linear phase have impulse response either symmetric or anti-symmetric. So in both cases we don't have to calculate all the coefficient. In fact, because this is anti-symmetric, so we just change the sign and we can easily do that. So as per discussion in the previous slides, that is specifically equation 50 to equation 53, they imply that structures for implementation, we need either m by 2 plus 1, m by 2, or m plus 1 by 2 coefficient multipliers rather than the complete or all the m coefficient multipliers of the general direct form structure, which we talked about in the on figure 29. So here we have drawn the structures implied by equation 50, and figure 33 shows the structures implied by equation 52, that is for m equals to even and m equals to odd respectively. Okay, so we can see that basically exploiting the symmetric conditions, we know that we have repetition of the coefficients, that is h of 0 equals to, like for the case of the symmetric right, a case that is type 1 m even, we can say that h of m minus, we just mentioned on the previous slide that h of m minus n equals to h of n. That means h of m equals to h of 0. So that means to calculate the structure, we need only almost half of the coefficients, right? So that means h of 0 equals to h of m. So at this point we have, for example, I have h of 0. Now we are delaying because we are just reducing in this exploiting this property, we are just reducing the number of coefficients required. So for example, at this point we have the coefficient h of m. So because h of m and h of 0, they are same, so the signal here will just be added with the signal here, right? The original signal and the signal delayed by m units, they are added here, and then they are multiplied by h of 0. Similarly, 1 unit delayed signal and the all delays minus 1 signal we get here, so we just add them and we scale them by a factor of h of 1. So if you look at this one, we can see that we just multiply it by h of 0, h of 1, h of 2, and up to h of m by 2 minus 1, right? So this shows that we have essentially reduced or almost half the coefficients. And this is a similar structure, but this is for the case when m is odd. Okay, but in both cases you see that you multiply the undelayed with the one with the maximum delay, then again next 1 unit shift this one, so 1 unit shift this one, and you just add these because based on the derivations you know that we have to add x of so for example, for the type 1 case, we say x of n minus k is added with x of n minus m plus k. So we have same number of delays, okay, but we have reduced the coefficients, right? So I hope that gives you idea. We are not reducing the delays. In fact, we are just reducing the number of coefficients that are based on the fact that for the linear FIR linear phase FIR system, we have the 4 types based on the symmetric conditions. From here we are starting a new topic, that is filters. Most of you will have familiarity or awareness. You might know what is a filter. So we can define it as a filter is essentially a system or network that selectively changes the wave shape, amplitude frequency characteristics, or the phase frequency characteristic are both of a signal. So you might have understanding that we have because we have continuous time and discrete time or digital signals and systems. So that means signal filters can also be continuous time, that is analog signal. You have well familiarity with the analog filters. I think you know that most of you have done this in your electronic courses or the courses on the circuits, that in general we can say the analog filters, they consist or they're made up of the main components that are capacitor, inductor, and resistor, or they may also contain an amplifier. And you have understanding that that can be a band pass filter that passes a band of frequencies and stops all the rest of the frequencies, or you have then the low pass filter that passes a frequency from DC up to a certain frequency that is called the cutoff frequency. Beyond that, it removes or stops those signals from coming. Similarly, you have a high pass filter where you from a predefined frequency called a cutoff frequency, from cutoff up to the infinity, all the frequencies are passed, and those frequencies that are below or which are lower than the cutoff frequency are stopped. So you have done, I think you have familiarity with different type of filters. Here we'll be talking about the digital filters. So some of the applications of the filters are noise suppression. You understand, filters can be used both in image processing and in signal processing. So in case of images, we have imaging devices that contain the noise, so we need to remove those noises from the images, or we have biosignals such as heart, brain, etc., or we have a lot of other signals where we have the noise and we have to remove that. So one of the application of the filter is the noise suppression or noise removal. Others can be the enhancement of the selected frequency ranges, such as equalizer for audio system, increasing the basses, or the edge enhancement in images. Similarly, removal or attenuation of selected frequencies, for example, removing the DC component of a signal, or removing the interferences at specific frequencies, for example, those caused by the power supply lines. And we also can have applications such as bandwidth limiting. I think we have just discussed about this topic while we were doing the sampling of continuous time signals. So we use anti-aliasing filter for sampling to ensure that we can also use a band pass filter to ensure that the transmitted signal occupies only its allocated frequency band. I hope you have idea about this one, or let's discuss about the allocated frequency bands. So just to give you just an idea, this is the frequency spectrum describing different applications. You might have heard about it, that we have like this is some AM radio frequency that is in kilohertz, but before this we have some frequencies that are allocated to different services. You know that all the frequency spectrum is divided into different services, and it has been allocated to different agencies, for example the police, fire brigade, and so on. So the lower spectrum is for those, although I haven't mentioned here, but just to give you, because you have familiarity with AM radio, FM radio, and those things. So let's just briefly talk about it. So the first here from the left side is the AM radio, amplitude modulated radio. You might have heard it, or you might have also seen, or might heard news or some programs on it. So it has 106 possible bands or channels, and it is from 540 kilohertz to 1600 kilohertz, and each channel or each band is of 10 kilohertz. Now when you tune a radio, basically you are tuning the band pass filter, and you are basically you are tuning the center frequency for the band pass filter. So if you tune it to say 540 kilohertz, right, so the filter will pass all those frequencies that are, for example, 540 to uh, uh, 550 kilohertz, right, because it's a 10 kilohertz bandwidth. So it will pass those frequencies, and it will stop all the frequencies that are below this, or they are higher than this one, right. Similarly, for the case of FM radio, frequency modulated, right, so here we have frequency range of 88.1. I think most of you have heard this one, right. So 88.1 to 108.1 megahertz, and they have around 100 channels or 100 bands, and each channel has a frequency bandwidth of 200 kilohertz. So I hope you understand. Because we have, you might know that we have a carrier frequency, and then we modulate, right. Then we have the frequency of the voice or the sound or the music that we want to transmit. In general, we can call it the signal frequency. So so in case of AM, the maximum frequency a signal can have is 5 kilohertz. So that's why if you listen to music on AM radio, you can see the difference between the music on AM radio and that which is transmitted on FM, because where it has very high bandwidth, so it can have very high signal frequencies. So that's why there's a hell of difference between the quality of the music on FM and AM. But you can see that if we look at this one, we have 106 channels. And how much is this one? That's roughly 1 megahertz, right? So in this 1 megahertz range, we have 106 channels. Whereas if you compare this one with the FM, so in case of FM, we have how much spectrum is allocated to FM. So it is almost 20 megahertz, right? So in 1 megahertz you have 106 channels, and here we have in 20 megahertz you have 100 channels. So similarly, we have other VHF TV, that is very high frequency, and we also have UHF, ultra high frequency. So I hope you get the idea that the spectrum is divided for different services, and for each service we have some certain bands, and to because all the signals, they are present here, these are electromagnetic waves. So to capture a signal you need a filter. So that's just about to give you idea of why it's important to have a band pass filter, right? Because we want to receive a certain signal or certain channel from a certain services, because these are just few of them. That is, we have the radio, the television, and the FM radio, but we also have the other services, like I told you, police or fire brigade, or so many other, military, and those. So all of this spectrum is distributed or divided for all of these services. So if you want to discuss about this one, because there are so many things we can talk about this one. So just to give you the idea why so in comparison with the analog filters, which are made using the capacitor, inductor, and resistor, or the amplifiers, and so on, the digital filters are basically mathematical algorithm, and they are implemented in hardware and or software. So digital filters have the advantages over the analog filters, or we just give you a brief comparison of the two. So digital filters are programmable. That means we can change the characteristic of the filters very easily. We don't have to replace the component, we just need to rewrite the program. They are also reliable and repeatable. So reliable means that their efficiency or their performance does not change with the temperature or environmental conditions. You might probably have experience with the analog filters that the response changes with the environment. Also, in case of digital filters, we don't need to fine tune them. They have superior performance in some cases. For example, in case of biomedical applications where we have very low frequencies and they are very effective at low frequencies also. Also, we can save the filtered and unfiltered data for further use. Also, from the development of the technology, especially VLSI, etc., we can readily make these filters, and to also they are very small in size, so their power consumption is also low, which keeps the cost down. Some of the disadvantages of the digital filters or in general digital systems are we mentioned here, but they are also not constant. They are changing with time, so most likely with the advent of further more technology, we might overcome these problems. So there may be the speed limitation. The maximum bandwidth of the signals that digital filters can handle in real time is much lower than the analog. Also, we have finite word length effects. That means filters are subject to ADC noise that we have to, because in general you might have idea that most of the signals of the real world, they are basically analog in nature, and to process them digitally we need to convert them from analog into digital, and after performing the operations we convert them back to the analog form. So we suffer from the finite word length effects due to the analog to digital converter ADC noise that results from quantization. Also, the design and development time for the digital filters is longer. So hardware development can be longer than the analog. But once developed, the hardware and software can be used for other filtering or DSP tasks with little or no modification. So these are some comparison, and we end the lecture here. Okay, so Allah Hafiz.